Welcome, everybody. Nice to see so many of you here. My name is Jonathan Heasty. I have the privilege of being the organizer of Catch the Next Wave. Thank you for attending. I also have the privilege of being the organizer of Oceanology International, which is, I'm sure most of you are aware, and you are all free to attend. Your badge gets you into it, but it's the world's premier event for ocean science and marine technology taking place Tuesday to Thursday in London's Excel in the Docklands, so please come along. We have not only more content to deliver across multiple streams, but also many, many thousands of people and some cutting-edge technology, including robotics and automation. So before I talk a little bit more and say a few thank yous, some housekeeping if you don't mind. May I ask you all to turn your mobile phones off or to silence to respect your fellow delegates and the speakers. If you hear a fire alarm, there is no fire alarm planned for today, but if you hear a fire alarm, it will be a continuous tone. I'd ask you please to vacate the building, out down through the stairs or out there, turn left and make your way out to Albemarle Street and congregate on the right-hand side, but there's no planned fire alarm. We are here in an amazing building with a huge heritage. The Royal Institution, founded back in 1799, I believe it was, and first came here in the year 1800. So they've been delivering and driving forward scientific excellence for over 200 years. It's amazing to see so many of you people here. We're all coming here today to focus on next generation robotics and autonomous systems. I'd like to say a thank you on behalf of the organisers and the committee to all of our speakers whose time and effort today is hugely appreciated. We're going to hear from people from across the marine industry, but also from aerospace and medical industries as well. I'd like to extend our thanks to our committee, our conference committee, who have spent many a year working towards shaping today's program, opening up their brains and their little black book of contacts to make today possible. So thank you very much to the committee. You'll find information about the committee members and our speakers in this program, which I hope you've all picked up. If not, grab one outside in the break. I'd also like to extend our thanks to our sponsors and our supporting associations. Without them, again, today it wouldn't be possible, and you will see their logos appearing around the building. But particular thanks go to BMT Group for their sponsorship, to X Prize, who you'll be hearing from later on, to the National Oceanography Centre in Southampton, and to Natural Environment Research Centre as well for their commitment in making today possible. I'd also like to thank the Society of Underwater Technology, the Institute for Marine Research, Science and Technology, and also to Marine Technology Society as well for their help in putting together today's programme. Last of all, before I sit down, I'd also like to extend our thanks to our two co-chairs who have been the driving force behind the programme, one of which you will hear from later on, who's Professor Ralph Rayner, sitting over there. Thank you, Ralph, for everything that you have done. And I would like now, if you don't mind, to introduce you to the other. His name is David Brooks. Please put your hands together for David Brooks. Thank you very much.
Thank you, Jonathan, for that introduction. I'd really just like to second a welcome he gave to everybody here for coming for what I hope is going to be a really successful day. This is the third event in a series for Catching Next Wave. The first event in 2012 was held here, and we looked at ocean science and marine sector and contrasted that with the oil and gas sector and introduced comparisons with the aerospace sector and the medical sector. In 2014, we're at the Royal Academy, and we had some interesting presentations there again, looking at the material science, looking at the aerospace sector, and contrasting it with deep ocean research. This year, we've got, again, a very distinguished panel of speakers, and we've actually concentrated this year on one of the really hot topics in the whole sector, which is robotics automation. We've taken a range of speakers from not only the ocean science, from the aerospace, from medical sectors, and we've actually, put together a comparison between these sectors. And the aim of the whole event is to actually stimulate discussion, to stimulate transfer of technology, transfer of ideas between these sectors. And I think we all have a real duty here to learn. As Jonathan said, I'm sure you'll be out networking in the many extended coffee breaks and lunchtime today. But I would really like to move on to the main agenda and our first two pairs of speakers. The first one is Gwyn Griffiths, who's going to talk about robotics, and I hope that we're going to have a second speaker, David Lane, who's going to talk about marine robotics. Gwyn is the ocean technologist and immediate past president of the Society of Underwater Technology, the SUT. His career began in the 1970s developing instruments with the National Geographic Centre, particularly Autosub AUV, for which I think he's most famous for. Throughout his career, he sought as a technologist to develop an understanding of scientific requirements for ocean measurements to ensure that the needs are met. He has a very distinguished academic career as Professor of Underwater Systems at the University of Southampton and is a prolific author and editor of numerous journals. His prizes and awards include the President's Award from the SUT and the Distinguished Technical Achievement Award from the IEEE Oceanic Engineering Society. Gwyn.
Thank you, David, for that kind introduction, and good morning, ladies and gentlemen. It's a great privilege to have been asked to give the opening talk today, especially here at the Royal Institution. As befits this historic venue, my charting of the rise of marine robots will start in the 19th century. I'm going to give you a few moments to try and puzzle out exactly what you're seeing in that top illustration. By the way, that picture is from 1895. Keep that in mind. The rise of marine robots is a collective endeavor. Throughout my own career and contributions, I've been enormously lucky to have worked with talented and dedicated engineers, scientists, technicians, administrators, suppliers, insurers, lawyers. I could go on, and by no means all are captured here. And my talk this morning is not mine, but it's really their story. For the framework today, I've chosen to use Geoffrey Moore's version of the well-known technology adoption life cycle. His book is a great read, and I'm really grateful to Mario Brito up here on the left for bringing this book to my attention. I really do commend it to you. His insight is that the classical curve, supposedly a smooth curve of technology adoption from innovators through early adopters to the early majority and then down to the laggards, is not smooth. But rather it has cracks and a major chasm between early adopters and the early majority. And the area under the curve, as it represents the available market, if you're a commercial supplier, you really do need to ensure that your new technology can meet the needs of the majority users. So why is there the crack and the chasm? Moore's insight is that they come about because of the characteristics of the different users. Now, of course, these text snippets here, these pen pictures, are caricatures. They are oversimplifications. I'd like to think of myself as actually working across the gap between innovators and early adopters. But I'll tell you, I'm a true laggard as when it comes to upgrading the operating system on my computer. So just because you fall into one category for one part of technology in one's life these days, doesn't really mean that you are that in your entirety. Moore's position is that the characteristics of the early majority mean that they pay little heed to the experiences of the early adopters. If I'm in the majority and I want this technology to work out of the box, am I going to listen and take heed of somebody that's really prepared to work with failures, who doesn't really care about documentation? They know the person at the company that made the invention. They'll just call them up. They don't need a sales desk. So meeting the needs of the majority users is going to feature strongly in my talk. Let's bring this to life with an example. In 2009, with two other colleagues from Southampton, I gave a 2-day workshop to the Royal Navy, about 25 staff, including technical and seagoing officers and enlisted men who would be working with glider technology. It was my job to cover the basics of the glider technology. What is a glider? How does it work? What does it do? No problem. My colleague David Smead talked about the science experiments that we had run. The ability to put the gliders in the water from a small boat a few kilometers off the south coast of France, have the gliders navigate their own way out to the observation site, to stay there for months at a time, and then to make their own way back. Yup, they got all of that. Fine. But my colleague Lucas Merkelbeck then gave the presentation on how you actually command the gliders and how you interact with them when they're there on the surface to send you the data. I looked at a sea of horrified faces. How on earth could they take this into their everyday use in their operational scenario when under pressure? Now, of course, any gap, any crack, and here was a true chasm, is an opportunity. And it's been an opportunity for third-party companies. So exemplified here in the UK by Seabite. They've taken this problem and provided solutions such that end users don't really care whose technology, whose coding they have to work with. They have a unified, simple operator interface. So a business opportunity to enable companies to cross this chasm. But let's return to the rise of the marine robots. What were you seeing in that picture, which is bottom left now in its original monochrome? It's taken in the Bay of Naples. Anyone hazard a guess? Yes, what you're seeing are two unmanned surface robots with self-steering equipment, and they are extracting their energy for propulsion from the wave field. Yep, all of that done, tick, 1895. Not at what we might consider a major technological laboratory, but at the zoological station in Naples. And Herman Linden, the secretary to the zoological station, was the inventor, and there he is, in a boat of his own design with flaps fore and aft. 1895, so this is before the Wright brothers and aerofoils. So they're simple flaps, not the most efficient devices, but my goodness, they did work. And there he is in a wave-powered boat. What do we have a century later? Linden called his vessels the Autonaut, and most AV has taken that name, the Autonaut, in tribute to Linden and his innovation. And now we have a wave-powered, environmental, scientific, commercial, and military platform of great promise with today's modern technology. What about another example of crossing the crack? I'd like to think of this slide encompassing perhaps one of the greatest achievements of my own career. We're looking at a very compressed timescale. We're looking at the middle of 1996 to the middle of 1998, just 2 years. I was enormously privileged to have worked with an incredible bunch of engineers, the Innovators in the top line, who from May 1996, with Autosub missions of 300 meters inside the dock, moved in essentially order of magnitude steps from a harbor to a sea loch to the current off Florida to 263-kilometer missions off Bermuda in the deep ocean in just 2 years. They delivered on the technology side, no doubt. But what about the crack to users? The Natural Environment Research Council that was funding this work, in parallel, and I really do stress, in parallel, constructed a program involving the scientific community for Autosub science missions, science underlined, not technology, science missions, and put that program in place and approved it in early 97. And that program was to include missions under sea ice in Antarctica. At that time, Autosub had covered less than 30 kilometers and never away from shore. That is true vision on the part of a funding agency and the scientific community to come together to do that in the knowledge that technology would deliver when it came to it. But the rise of the marine robots isn't just a story of scientific research community. There have been true early adopters and champions in industry, and perhaps no more so than Thomas Chance of CNC Technologies. So in 2001, 2002, CNC Technologies adopted the Hugin AUV, made and manufactured by Kongsberg, and brought it into commercial service. And of course, that followed many years of experience with autonomous underwater vehicles by the defense community. And in August 2003, Thomas presented this graph at a meeting I was at in New Hampshire. I admired his brutal honesty, because this showed that when he took delivery of this commercially built vehicle into his operational scenario in the Gulf of Mexico, the vehicle was available at best 50% of the time that he wanted it. And his quote here, that transitioning into commercial AUV surveying proved to be an expensive and exhausting challenge for CNC. So this is an example again where despite the early adopter experience with science and defense, commercial users found it expensive and exhausting. You'll also see the dips in 2002, very clearly associated with upgrades. No wonder I'm a laggard when it comes to upgrading. It really does hit your reliability. Let's look at a more modern example of innovation and the long haul. And my little sketch in the top left there is just to show that the peaks and troughs and the splitting up of innovation. It doesn't always go in a linear, smooth progression, as some people might expect. And there in the top left underneath that, I'm delighted to say that this is with permission of Doug Webb, to include this from his engineer's notebook of the 8th of February 1986. We can put a precise date on when Doug Webb came up with the idea of a thermal engine to capture the energy of the thermal gradient, the temperature gradient in the ocean. That's what came to him on the 8th of February, and then on the 10th of February, he saw how you could use it. And he could use it in a profiling glider, an underwater vehicle that would go from the sea surface down deep through that temperature gradient. February 1986. And Doug was well supported intellectually and through funding by the US Office of Naval Research and others during this time. 1991, glider with a battery buoyancy engine, an interim measure while the thermal engine gets refined, was tested. Then the thermal vertical profiler. Let's do it in the vertical. Let's not worry about gliding yet. Both come together in 98. Thermal glider, debut in the open ocean, 2007. 2008-9 further missions. In 2015-16, we now see the vehicle as the Slocum E-twin thermal in a collaboration between Teledyne Webb and NASA Jet Propulsion Laboratory. And I think it's fair to say that this is not yet a fully commercial product, and I may not even need the word fully, from innovation in 1986. But you'll recall that in 1991, as an interim measure, there was a glider with a battery buoyancy engine. So why not go back to the battery buoyancy engine while you refine the thermal? And indeed, that's what happened. But really, it was not until 2002, 2003 that this became a commercial product. And I'm indebted to Teledyne Web for sharing their sales, their annual sales, unit sales, from 2002 to last year. And the expectation this year is that sales will at least be equal to that of the last few years. Now, this looks like a nice, smooth progression after a significant lag. So let's not forget the lag in innovation from 1986 till 2002, before it was a commercial product. But I think this was anything other than smooth. Clayton Jones, who's here from Teledyne Web, can give you the details. But in my book, it was only the acquisition by Teledyne Technologies of Web Research that gave them the resources and the know-how to be able to transition to winning a US Navy contract for 135 full production rate gliders after delivering 15 earlier examples. So moving towards that early majority user required acquisition of an SME by a large company. Let's now look towards another robot technology in the oceans used by a widespread majority. And this is perhaps the simplest form of ocean robot, the Argo profiling float. Over 11,000 floats have been deployed to date. That's a tremendous success story. This is a graph from Durack et al. Last month in Nature Climate Change. He and his colleagues fear that from this year onwards, so 2016, in the grey lines that project the expected future number of these floats to be deployed, that this is decreasing, and that from 2018 onwards, these authors' projections are such that the 3,200 active floats needed to maintain the array will not be met. And in his quote, this is the biggest challenge of the Argo array, is to keep that 3,200 floats as we now have varying pressures on budgets and so on. But the rise in the number of papers drawing on Argo data continues unabated. This long experience with the profiling float lets us look at various aspects of technology evolution and competition. We see the rise of two-way communications of iridium there in light blue, displacing Argos. We see the rise of competition. There are many other suppliers as well, but it would get a crowded graph. So we see the erosion of the dominant supplier. We see the rise in competition, indicative of a mature market. We see the introduction of meaningful warranties. You'll get 100% credit from Seabird if their float does not give you 100 profiles. Too early in my life, I would get a warranty for an instrument where it was fine until I put it in the sea. What use is that to an oceanographer? How has float life cycle improved since 2001? This is the rise of reliability and technology. So this is a graph, percent of the number of floats deployed in any year that with the number of life cycles, and each cycle, data cycle, is 10 days. 150 cycles is a 4-year life. Let's move through from 2001, 2002, 3, 4, 5, 6. This is a brilliant tale. Up from 5% to over 60% of floats deployed in 2006 achieved 150 cycles. Combined efforts of users and manufacturers delivered this. There's the 2006. It was a peak. 2007, 8, 9, drop. Why? Some improvement for those deployed in 2010, 11. Those deployed in 2012, bit of a mixed story. But that grey line, 2012, is the one lowest reliability for the last 6 years. Now, thankfully, manufacturers and the user community are getting together. They have initiatives in place, and they've got others planned to understand the root causes of these early failures in floats and why the improvement to 2006 has not been sustained. But oddly enough, those were global averages. What about so-called expert groups? Some groups that deploy floats essentially get kits from the manufacturers and they build them themselves. In staff time, that costs them more, but it actually delivers them a far longer life. So this one group, who shall remain nameless, achieves an 80% float life at 150 cycles over the last 5 years. So the experts, the early adopters, still have value to add to the majority users. Oh, that everybody could rise up to the performance of the best. Another factor that really impacts the majority users is utilization. What's troublesome about this picture? There are 31 marine robots on the quayside, not in the water. Yeah, that's troublesome. Few groups share data on the utilization of their gliders. And gliders are perhaps the most used of the truly autonomous underwater vehicles. And I'm really grateful to Rutgers University, the fact that they share this information on their website. And John Kerfoot and others have provided me with updates to this information and have aided my understanding. But along the bottom there, you see the names or numbers of various gliders from Rutgers and their associates who they help with glider deployments. And the vertical axis is the number of deployments in total. There are a few gliders that are real heroes. RU-05, brilliant, 40 missions. But there's a long tail there. And last year, for example, only 24% of their fleet was used at least once. Oops, wrong way. What about the total distance covered by those gliders? The top graph is the Rutgers experience. And this is a warning for those that project from 3 data points. 1, 2, 3, up, off the graph. No. In fact, 2007 was almost the peak. And since then, I'd like to think that it's a plateau between 15,000 and 20,000 kilometers per annum. This is not just one organization. I stress that. So from Southampton in the UK, the early experience, 3 gliders, and their utilization rose as the, over on this side, we have the kilometers per annum increasing. And again, we've got 4 data points, and now we know, of course, let's not project that forward. Let's come back here a few years' time and see what's happened. But the utilization rate in green there from the current fleet is less than 15% at Southampton. It could do more. These are not technological limitations. There are other factors at work. In my closing few slides, I want to return to the importance of vision. In 1989, my group, then at Wormley, before moving to Southampton, commissioned this painting to capture our vision of autonomous underwater vehicles gathering data beneath an Antarctic ice sheet. It would work under the ice, it would come out into open water in summer and telemeter its data back. By 2005, 16 years later, that vision had started to be delivered. Autosub 2 gathered this Swath bathymetry image of the underside of the Fimbul Ice Sheet in Antarctica. This is the one it came back. The next one it didn't. The smooth ice, seen here, was fully expected. The scientists expected really a boring data set, anything but. They did not expect this rough topography on the scales of tens of meters in the vertical, it changed their views on what melting processes occurred underneath these ice sheets. So technology aiding science. The vision was fully delivered in 2009 and then 2014 with a series of missions and campaigns under Pine Island Glacier in Antarctica. Pine Island Glacier is Antarctica's fastest melting ice sheet. There we have the cartoon in the top left, and underneath it another graphic that shows the missions in that cavity in high summer. Those missions showed why Pine Island Glacier is now in self-sustaining retreat. It will now retreat for at least 200 kilometers towards the South Pole. That data came from this mission. But that mission also shows us the state of the art in collision avoidance technology. This is an AUV that has no communication with the ship. The ship is at 60 kilometers away in open water. The AUV is under hundreds of meters of ice. It has to look after itself in an environment that we don't know entirely. We think we may do, but we don't know. So I'm going to show next an animation of the track where the vehicle will run through towards the turning point, which it reaches at minimum headroom near where the glacier grounds. It's followed the seabed in, then it'll follow the underside of the ice as it comes out. We'll see indicators here of the range up above, ice up above. We'll see a forward sonar for collision avoidance in case there's any ice ahead. And the X is the klaxon going off, collision imminent, do something. So this animation is going to run through quite quickly. Going in, no problem. There are two vectors at the head of the track, red and green. They're aligned, commanded an actual heading. There we see, there's the turnaround. The vehicle responds. It's following underneath the ice, but then the ice overhead disappears. Why does it disappear? And now it's failing to turn back. The vehicle has found itself in a crevasse. It tried to turn round, but it couldn't. But it then knows enough such that in that situation, it knows that there's open water clear of ice deeper down. And it knows, I better get down there, which it did, and then it turned around, and then it came back home. And that captures, I think, the state of the art in collision avoidance and vehicle behavior that we see today. And my closing slide takes us to the Pine Island Glacier Autonomous Observatory of 2025. We're not now just leaving those vehicles there for a few days in high summer. We're taking them there in high summer, leaving them for at least one or more winters. They'll have sufficient energy, they may need to hibernate, but they will observe through the year. And some of you may recall my talk 2 years ago on the importance of Nyquist and sampling through the year. That has to be done underneath this glacier. They'll need to telemeter using radio through the ice sheet. They'll snuggle up. There'll be a gateway on the ice to translate those radio signals into SATCOM signals, so you'll get your data from those vehicles beneath the Antarctic ice sheet. And that, ladies and gentlemen, is not only a vision for Antarctica, not just a vision for Earth, but off this planet, which we'll hear about this afternoon. Thank you.